In Unit 2, Linear Motion and Waves, Topic 2 is on waves. Now when we're looking at waves, we're not just talking about waves at the beach, we're talking about the physics principle of a wave. Now the first thing we need to note here is that a wave is something that transfers energy from one place to another. And the other critical thing associated with that, though, is that while it's transferring energy, it's doing it without transferring matter. So we don't have anything that's sort of a particle that's moving along that is causing the energy to be transferred in, say, kinetic energy of the particle. We're looking at how energy can be transferred without the transfer of matter. So that's the first thing to keep in mind about waves. So basically just sort of a definition of waves. Now there's a few different classifications I suppose we need to be aware of here. The first one, so a very key point about mechanical waves. So most of what we'll be dealing with to begin with is about mechanical waves. So a mechanical wave is one that requires a medium. So one that requires a medium, and by medium we basically just mean a substance. So it's sort of a bit of a technical term. So it requires a medium to travel through. So if you think about some of the more common waves that you'll have come across, things like sound, so sound waves require air or some other substance to travel through. Seismic waves from earthquakes travel through the earth itself. So a few different examples there where matter is needed for the wave to be transferred. Just as a side note, the alternative to a mechanical wave is an electromagnetic wave. We'll get into electromagnetic waves a little bit further along, so I'll just briefly mention it now, and we'll deal with it in much more detail at a later stage. An electromagnetic wave does not require a medium. So you might sort of think, well, hang on, how can a wave travel if it doesn't have something to travel through, which is where electromagnetic waves become important. Because they don't require a medium, though, that means that they can travel through a vacuum. Now, really quickly, when we're dealing with electromagnetic waves, we're actually dealing with electric fields, or electric and magnetic fields. So a little bit above the scope at the moment of what we need to deal with, and so we won't really deal with it quite yet. We'll talk a little bit more about it later. An obvious example there, though, is light. We get light from the sun. There's a vacuum between the sun and Earth, so we can have light travelling through the vacuum of space. Okay, so there's a couple of classifications. We're now going to move on to another couple of different waves that we need to be aware of, and we're going to focus specifically on mechanical waves here. These ideas will still translate across to electromagnetic waves as well, but we'll start off just looking specifically at mechanical waves. Now the first type of mechanical wave we need to be aware of is a transverse wave, and we'll look at a simulated wave here to describe some of the key points about transverse waves. So to represent a transverse wave, you can imagine this blue line is representing, say, a string or a rope. We're going to pass a wave through it, which would look something like that. Now, in order to demonstrate the idea behind a transverse wave, we're also going to, we're just going to go back and look at individual particles that exist on the wave. So those little dots representing a particle in each part of the rope. So if we were to then pass the wave along in this sense, you can see then that the particle motion of the compared to the wave direction. So if I follow a crest along here with with my pointer, you can see that the wave is moving to the right. Meanwhile, the points are only oscillating up and down. So if we highlight this red one here, we can see that as the wave's moving to the right, the points themselves are only oscillating up and down. So the way that we can define what a transverse wave is then is that it's the motion of the particles is perpendicular, or motion of the particles in the medium, I should say, is perpendicular to the wave direction. So that gives us the definition of a transverse wave. And some examples of that sort of scenario would be things like the vibration of strings, so any stringed instrument, whether it's a guitar or a violin or any of those sorts of instruments. Another example would be S waves in earthquakes. So as earthquake waves travel, one of the types is an S wave, so it causes that transverse motion of particles in the earth. Now there are some points that we need to identify about the transverse wave, as mentioned in the animation that we just saw, so I'll just notate them now. So the first thing to identify here is that we have what we call the equilibrium position. So I'll just draw that line in first of all, so running right through the middle. So that equilibrium position is an important one to have a good understanding what it's about. So I'll just start with that point first, or that part. Now the equilibrium position, if you think about the word equilibrium, it means that everything is balanced. And so the equilibrium position there is the point at which the particles are at rest. So when the particles are at that position there, we'd consider that to be the equilibrium position. And another way to think of it there is that it's when there's no wave travelling through. So if there was no wave travelling through this particular medium, then the light blue line there is where where all the particles would be positioned. Now a couple of other points to note. We've got this point at the top here. We call that a peak. Another word that sometimes gets used there is a crest. So basically just indicates the top. And then down the bottom here we have a trough. So sort of the bottom of the wave itself. Now the other thing to note, we saw that the direction of the wave was to the right. So we need to be clear on that. So that's the direction of the wave. But at the same time, let's say we go back to this red particle, we saw that the red particle was simply moving up or down. So those lines there represent the direction of particle motion. So we can see there that the particle itself is moving perpendicularly to the direction of the wave itself. Now the second type of mechanical wave we need to look at is a longitudinal wave. And again, we'll have a look at an animation here to identify some of the key things about longitudinal waves. This time for a longitudinal wave, we're going to use vertical lines here to represent what happens with the motion of particles for a longitudinal wave. Think of these lines as, say, representing the coils of a slinky, and we're going to be moving the coils backwards and forwards in order for a wave to be transferred through it. So if we have that wave being transferred through, you can see there that the coils themselves, as I said, they're moving side to side, backwards and forwards, as the wave travels along them. So again, if I trace along with this compression region, we can see that the wave is moving to the right. But if we look at a single coil, say this green one here, you can see that it's just oscillating side to side, backwards and forwards within a defined range of motion. So the definition that we can write for longitudinal waves is that the motion of particles in the medium is parallel to the direction of the wave. So as the wave's moving through, the particles are actually moving in that same direction. Now, the most obvious example of longitudinal waves would be sound waves. So that's a scenario where the air particles, say, are vibrating backwards and forwards in the same direction of the wave. We'll have a look at a few specific examples of that in class. And the other one, coming back to earthquakes again, would be P waves. So they cause the motion of the Earth to sort of oscillate in the same direction as the wave that's travelling through the Earth itself. Again, let's just have a quick look at some of the particular parts of a longitudinal wave, and we'll just notate those. So on our diagram here, first of all, we'll go with the idea here that, not the idea, the direction of the wave being to the right. So we saw that the wave was travelling to the right there, but the particle motion, so of this green line, it was simply moving backwards and forwards. So those arrows there representing the direction of particle motion. You can see there that they're parallel to the direction of the wave. Now the next thing that we need to identify is this little region here. That's known as a compression. So the particles in the medium are being squeezed together or compressed together. Alternatively to that, we then have this region here that we would call a rarefaction. So R-A-R-E-F-A-C-T-I-O-N. So rarefaction relates to the word rarefied. So the particles are being rarefied, they're being spread apart there. Now it's difficult to represent the equilibrium position on this diagram because the particles are sort of moving side to side, and so it's hard to see where it is. In order to make the comparison there, though, we'll have a look at both longitudinal and transverse waves side by side in an animation instead. So if we now compare longitudinal and transverse waves, we've got both of them on the screen now. You can see here that the equilibrium positions of both the red dot and the green line are aligned. So they're both at equilibrium in the same position there. If we then have a wave being transferred along both of them, first of all you'll notice that the speed with which the wave is moving, so if I trace the crest of the transverse wave along and then compare it to a compression of the longitudinal wave, you'll notice that they are the same speed, so they're moving at the same rate. Now, if we look at the movement of this green line here, you'll notice that it's fastest as it's moving through both a compression to the right and a rarefaction to the left. So a compression and a rarefaction, they don't actually match up with peaks and troughs of a transverse wave. They match up to where the particle is travelling through its equilibrium position. So if you compare that to the motion of the red dot here, you can see it's moving fastest when it travels through its equilibrium position, and when it's at its maximum or minimum displacement, that's where it has it's momentarily stationary. So compressions and rarefactions actually correspond to particles moving through their equilibrium position. If we then go down and look at the transverse wave, you'll notice that the crest occurs when the particle has moved its greatest distance from its equilibrium position. So the crest being at the top there, trough being at the bottom, and so the motion of the particle, as I said, at that point is just temporarily stationary. So for a very brief instant in time, the particle is not moving anywhere. And so we can see that you can sort of line up that the peak as we move through here. It's sort of halfway between a compression and rarefaction in a longitudinal wave. Likewise, if you then sort of flip it around, look at a compression, that actually lines up with the sort of the downward slope of the transverse wave, and the rarefaction lines up with the upward slope of the transverse wave. So just something to keep in mind that strictly speaking, a compression doesn't match with a trough. It matches with that sort of downward slope.